So that's okay, we just probably just keep moving everything scheduled for 5 or 10 minutes, so we'll figure out how it goes. Our next speaker is a really famous person in machine learning, okay? Alex Smola, who actually will be starting with page 1.5. He got PhD in physics. He got PhD in physics, which my physics means everything in my generation, right? Chemistry is called applied physics. Biology is physics, but wherever can move. Right? That's very simple tool for physics. So physics is everything. So you got degree in physics, that's bias anyway. From University of Technology from Munich, and University, got PhD from University of Technology in Berlin. Then he went to academic job, I think somewhere in Australia. So Australian National University, being a professor, doing really great. 2008 he went to Yahoo, and then 2016 became director of machine learning and Amazon Web Service. I personal bias, I don't like the word machine learning. I think it's more like automatic learning. Machine don't learn anything. So anyway, by that, interesting thing is when you look at his website, my final comment, you go to his website, give a name and address. Without saying anything, you say, I'm currently not looking for a PhD student. So see, you must do lots of comments rather than say how wonderful I am. You say I don't need more PhD. So by that, let's welcome Alex.
So thanks for the kind word and the introduction. The reason why I'm not looking for PhD students is simply that Amazon doesn't take PhD students. And yeah, sorry, don't be waste their time on that. So this talk forced me to, well, think back a little bit. We've been doing some work on graphs, mostly my team in Shanghai has. So a lot of the results are due to Zheng Zhang, Dan Zheng, and Mingyue Wang. Also part of the team in Palo Alto. But this talk sort of forced me to go back and look at, what did we do with graphs before? And so, okay, a little bit of a bait and switch on you, because I say, well, from features to kernels, to features back again, and I will take a little bit of, engineering on you in the end. So talking about, frameworks, backdrop, that you take graph backdrop partitioning, and stuff that are involved in this. And so, but let's start with something very non-threatening. Okay, well, yeah, Russian politicians. Okay, sorry, not threatening, maybe the wrong word, but so they do stuff with each other, right? And so you might want to do interesting things with that network. So for instance, you might want to find out what the relationship is between two vertices. You might want to find out, what the attributes of a particular vertex are. So such as you get some features, maybe you get some additional data, maybe you know the net worth of that person, maybe you know what time they send messages to each other and so on. And well, maybe in a slightly different setting, you might have a social recommender. Hey, you might want to take a bribe from that guy too, or well, don't trust this one. Or maybe use additional data, maybe biographical data to combine this. So that's the kind of fun that you might want to do with graphs. You can also use that for drug discovery and so on. So the big graphs are really everywhere. To some extent, I would argue that probably we have one of the largest places of graphs available. Yeah, I know. I didn't make that graph, but yeah, I would have wanted to put him in, but last time I did this after that, he got elected. That was in 2015 in that KDD talk I made fun of Trump, and he got elected. So it went badly. I don't know what happened. But
was that based on real data?
No, this is just like, this is an interaction network of Russian politicians that I got somewhere, but this is just to motivate the problem so far. So what do we really have? Well, we have some vertices with attributes and edges with attributes, and then we have an estimation problem, namely given some vertex labels, you estimate the remaining ones. So for instance, who can I trust, who I cannot trust, or given some edge attributes, well, can I make some more? So for instance, which additional edges should I add, maybe they're timestamped and so on. So, and let's just simplify this even further. Regression on a graph. So this is like vertex labels, like yi and y, and I want to find some function such that the function is kind of taking this a little bit liberally because I have fixed number of vertices. At least in the simplest case, it's really a vector. But let me just call it a function for now, which maps the vertex ID into fi. And then I want to, for instance, minimize the loss, like the least squares loss. So fi minus yi for wherever. And so that gets me to a number of problems, like how do I infer the function values on previously unseen vertices, and how do I even define smoothness on this? And so one thing that I could do is I could just say, well, let me do feature engineering, right? So I have maybe some linear function, fi is w transpose vi plus b, and all the intelligence is now in those vertex features. And I could do a number of things, like the number of neighbors tells me something about how important somebody is. So I could just look at the degree, maybe the degree of the neighbors and other things. I could look at a lot of different subgraphs that I can get. Let's say maybe I take a 5-hop subgraph and I get an entire vector of that. And that's walk to vec, for instance, and people like this. Or I can just overall fingerprint the k-step neighborhood, and actually the Weiss-Feller-Lehmann algorithm is a really great tool for that. And Carsten Workwart and Nino Shabashidze in their prize-winning paper, they use that to very efficiently compute graph graphs. So we'll get to the Weiss-Feller-Lehmann algorithm in a little bit, but it's actually an amazingly clever algorithm. Or I can just use linear algebra heuristics. It's not uncommon. Maybe I take my graph connectivity matrix and I factorize it, and maybe I take the leading few eigenvectors and I get some idea of what might be in there. Or I use PageRank, and PageRank turned out to be a multi-billion-dollar heuristic, namely the amazing heuristic that led to Google web search. And so I can do that. As an alternative, I can look at smoothness over edges. So I basically compare with some function gamma adjacent vertices, or maybe look a little bit further. And I can use Laplace smoothing. So the Fiedler vector and so on. Jump did some interesting work on that. So I can basically sum over I and j if I minus j squared, and then by simple trigonometry, that's just f transpose d minus gf. Forward. And if I don't like L2, I can try an L1 version. And so Fuchs1 and Line Fuchs-Rani, and I happen to also sit in on the meetings, but it was really Fuchs1's work. You can do trend filtering on graphs, and you can look at higher order derivatives there. And this works quite well, right? I mean, it's this. So basically, at least you can construct data sets and situations where the L1 version beats the L2 version. Okay, so nice story, but it's expensive. So let's take a little bit of a detour. Once upon a time, there were kernels. So what does the graphical clustering have to do with kernels? Well, I guess that's the obvious part, namely, so what I can do is I can look at smoothness, and since I can use the graphical clustering as a measure for smoothness, well, okay, I can, maybe think whether I could design some kernels based on that. And this, generalizes the finite differences, for instance, for a mesh, you have, the
very well known to the field of mainstreams, just to put it that way. So, okay. So they told it, but maybe not. So the data I'm going to be talking about come from this project called Argo project, and the data collected by these cylindrical objects called Argo floats. And these floats would constantly engage in this ascent motion, and the cycle takes about 10 days. But once it goes down to about 2,000 meters, it starts to come up, and in that process, it collects temperature and salinity. And once it comes to surface, the data be transmitted. And there are thousands of, and it does this continuously. And there are thousands of floats, 4,000 roughly. Here's a picture of where the floats are a couple of days ago. This picture is renewed every day on the Argo data site, project site rather. So there are this many floats on that day. You would think that there are a lot of floats, but really, in view of the vastness of the ocean, really, we still have very sparse data. For example, here in the South China Sea, there are only a couple of floats, which is kind of surprising. The floats are free floating. They're not attached to any fixed station, anything like that. So they do move around, perhaps not too much. Now the name Argo came from Greek mythology, in which this person, figure, Jason, sailed in a ship called Argo to capture the golden fleece, grown on some winged rams, something. And nowadays we have the Jason satellite, which surveys the ocean surface, the topography of the ocean surface, and the floats look at what happens underneath. Now, this picture shows the growth of the number of profiles. A profile is the set of data that's collected in a cycle. So we have, every 10 days there's a cycle. So 3 cycles per float, 4,000 floats, so about 12,000 profiles every month. And as you can see, the number of profiles has doubled from since 2007. At that point, we had about 6,000 profiles. Now it's about 12,000. And the number of observations, so this is a histogram of the number of observations in every profile. And as you can see, the node is around 50 or 60. Now, here's a picture of plots of temperature versus depth at 6 different locations. So every location, the plots are, the profiles collected during the past 10 years or so. Generally speaking, temperature goes down with depth, but at very close places like here, this is a location that's close to the, perhaps close to Antarctica, and the temperature does go down first and then come up a little bit, and afterwards it will continue to go down. And also you notice that the shapes of these curves are distinct. They're different from location, somewhat different from location to location, except perhaps for this one. So all the curves are banded together in these other 5 locations. So we're going to be focusing on the relationship between temperature and depth. Although salinity is also collected, we're not going to address that. That's less important. Temperature is more important. And we're going to take a functional data perspective. But we're going to be focusing on estimating, modeling the relationship between temperature and depth, and estimating the mean function, for example. Okay. If you're interested in the Argo data, I can recommend at least two papers. This paper is written by two oceanographers, and this is very widely cited, which talks about the history and generalities of the Argo project and the Argo data. And the data is still not very well known in statistics. So there's at least this paper by Mike Stein and his postdoc, former postdoc, Mikel Vasella, who's now at CMU. I learned about Argo data from Mikel a couple of years ago when I visited Chicago. So that's at least a place to start. Now, let me talk about data a little bit. So, so the data in the measurements in the eye profile consist of these elements. So you have spatial location, which is longitude, latitude. You have time, which is day, year, actually hour of the day, which I ignore for now. And number of measurements, temperature and salinity measurements in the profile per cycle. So X denotes salinity, Y denotes temperature, and Pij denotes pressure, and the unit for that is dbar decibar, and that's roughly the same as meter, and that's a proxy for depth. Okay? If you have questions about the data, let me know. So we're going to focus, like I said, we're going to focus on temperature here. And for convenience, assume the flows are all identical, so we're going to ignore flow identity and just focus on profile. Okay? Now, so the model for the eye profile, so this is temperature again, is going to be a mean function, a mean field, plus the zero mean process, plus measurement error. And this zero mean process captures the dependency in depth, spatial location, and time. Right? So it's a really high dimensional process. The mean field is something, of course, everybody's interested in, especially practitioners. If you want to know if there's global warming, then the question to ask is whether this function changes when time changes. Right? So right now we're going to discuss a little bit of inference on the mean field, and in parts 2 and 3 we'll talk about the kind of models that are feasible for Z. Okay? So the three parts are connected this way. I already mentioned that we're going to approach the inference of the mean field from a functional data perspective, and we'll estimate this as a function of pressure. P is a strange notation for an argument of function, but it stands for pressure in this case, and it makes sense. We need to do some modeling due to the high dimensionality of the problem. So we're going to assume a very naive model. The mean is equal to baseline mean, which only depends on spatial location, but not on time, not on day or year. And here, the effects of day and year are assumed to be additive effects here, which may not be entirely reasonable, but that is sort of the best we can do right now because of the computational challenges. So mean D, the day effect, is modeled in terms of a periodic function, which sort of makes sense. It models the seasonal effect within the year. And then the year effect is just modeled very simply by this very simple quadratic model. It could be more complicated, but because we don't have many years of data. We have 10 years or 12 years of good data. So a qubit model seems reasonable, but in time, we will try to make this more complicated, more involved. Now, so since I'm going to be taking a functional data perspective, I'm going to be doing non-parametric estimation, and I need to assume that these functions, these are all functions in P, in depth. So I'm going to assume that these functions are smooth, at least 2 times differentiable. And I'm going to put all of these elements in a big sum of squares, like this. So here I'm assuming a fixed location, S naught. And so Yij is the profile that was observed at a location Si. So we'll make sure that we only include profiles for which the location is close, relatively close to S naught, where my estimation takes place. So I'm using the kernel function here to determine what data to include. Okay. Now these terms are exactly what I had here, except I'm now using different notation. So beta d is this periodic function, and beta y is this cubic function. Now, to estimate the grand mean, which is this guy here, I'm going to do a Taylor expansion, function Taylor expansion, to account for the fact that Yij is observed at Si instead of S0. Okay. Now, if Pij is not a vector, this is one point, P. I think everybody will recognize what this is. This is local linear regression. Right? Well, the complication here is I have a vector piece, and that's a fixed piece. And I want to make sure that these functions are smooth. So the functions, the quantities in red are functions, and they're the ones I'm estimating. So I'm assuming these functions are smooth, so let me just add a penalty to all the betas. So as you can see, this is a kind of a hybrid approach which combines local linear regression, kernel local linear regression, and a penalized approach. Right? And the minimization takes place in a function space. And so far we try to solve the space. And the penalty is simply the integral of the square second derivatives. And I have a whole bunch of those. So in order to justify local linear estimation, I need for the mean function to be Krishnaiah differentiable, which we do. And this approach leads to more efficient use of really sparse data in this non-parametric problem. And moreover, the information about the direction, the speed of temperature change is actually captured by the gradient. So the gradient of the mean function comes out as a byproduct in non-parametric estimation, and it's actually useful. It has meaningful physical interpretations, and I'll show you a picture in a moment. Of course, it's extremely challenging to really select the the smoothing parameters, the H, the lambdas, in a principled way. I'll talk a little bit about that in a minute. But we managed to sort of improvise and come up with reasonable choices, somewhat manually, if you like. And so we're just going to show you a picture of that. Here, this is depth from 0 to 2,000 meters below. And this is day of the year for one particular year, I think 2016. So this is a location in the South Pacific Ocean between Australia, Antarctica, and Argentina. And here are other Q estimates. So at every location there is such a picture. Okay. Now let me show you a picture of the gradient that came out of local linear estimation. Remember, we had a function in t, so for every p there's such a picture. This is a gradient field, and you see these arrows. These are directions of the gradient, so directions where temperature change is the fastest at every location. And the color here is the heat map of the magnitude of the gradient. Okay. Because I have such a picture for every pressure level, I can play a movie. So this is a movie of that as the depth changes. All right. Now, intuitively, there's some connection between how quickly temperature changes, that's the magnitude of the gradient, and the speed of ocean currents. I don't know what exactly the connection is, but intuitively there is such a connection. So on the upper left, this is a satellite picture of sea surface current speed. And using the same coloring scheme, I'm plotting three plots of the gradient field at three different depths, 300, 400, 500 meters. And somehow they're connected. For example, the details that you see here, you also see on the satellite picture. Now, unlike the satellite picture, which can only look at current speed on the ocean surface, we can go down below the ocean and look at the gradient fields for temperature change. So there's no objective so far. I'm really at a stage where I'm just exploring data, understanding data, and trying to explore the different methodology. And I will mention a little bit the objective. I'm far from the objective. Maybe in 5 years I can answer that question. So what's ongoing? We're trying to, like I said, we're trying to understand data and experiment with different approaches. The smoothing parameter selection is the biggest challenge we're facing right now. The solution of the approach I showed you earlier is a natural slowing, and there is a way to compute that, but still the computations are very challenging. Grace also taught us how to use the Lee one-mile formula to compute the optimal smoothing parameter. But again, it's very challenging. We're leaving a profile out every time, and dimensionality of the problem is so high with 6 different functions that we estimate. So we're still very much trying to grapple with that.
The smoothing function for each variable, and you're going to have
So it's, go back here. Right, so these are the functions that we estimate. And there is a lambda for each one of these. And of course, we have this h. So lots of smooth parameters to choose. Okay. Now, come back to what Dan said, it's really scientific issues that are the most important here. We want to be able to take part in climate research ultimately. So what we have to do at this point is to, for example, go to Scripps and talk to the scientists. And I view the work we've done so far as preparation for that, because they're very, very smart people. And if we don't have something to show for it, something to convince these people that we can contribute, they will not talk to you. And so I feel that we're close to the stage where we can go and say, can we come and chat? Like maybe they will be interested, and in a couple of years I can come back and tell you what we have accomplished in terms of real science. But so far, this is just a lot of exploration and trying to feel things out. Okay, so this is the first part of the talk. Now, the second part has to do with thinking about what are some of the suitable models we can use for Z to capture dependence. The first model comes to mind, which is really not a model, but stationarity. Can we use a stationary process to do this? Recall that I'm taking a functional data perspective. So let's say we have a process indexed by R. Now in our problem, it's really indexed by R raised to the main powers. But let's just make life simple and consider a class of processes indexed by t. So for every t, xt is a function. It's called a random element in Hilbert space. Right? Assume mean zero, finite variance. Define the cross covariance operator. This notation, tensor product notation is just outer product. So you can think about a finite dimensional situation. This is just, x of s times x of t transpose. This is cross covariance matrix, and it's called operator here because H could be infinite dimensional. And here I'm going to assume that X is second order stationary, meaning the cross covariance operator only depends on S minus T. Right? And that denote the stationary covariance by K. The K of H is the cross covariance between X of S and X of S plus H. So what are properties of H and what are some of the possible models? Seeing the complicated question, well, fortunately we have math. That's what math is good for. We have what's called Bachner's theorem, which would give us all the models we need, all the models in the world. And let's consider the simplest case where H is really one-dimensional. H is space complex numbers. And then this is what you learn in a probability class. This is a representation of characteristic function. Right? Now, suppose H is d-dimensional, C to the D, then things are more complicated. So for example, the non-negativity that we have here as real numbers now it is non-negativity for matrix. Right? Everything else remains the same. In that case, we still have Occam's theorem, which looks exactly like before, except that mu here is going to be a matrix of sign measures that are non-negative definite. Okay. Now, so next thing I'm going to do is to say, let's go to a bonafide function space and see what happens. And really, the story doesn't change very much. It's there's some background information you need to know about infinite dimensional spaces. So here, K is a collection of trace class operators with whose single values are similar, right? And we have non-negativity, as in the matrix case, was operator non-negativity. Continuity, we have to say what we mean by that. So this is in terms of the tracing norm as 0. And then we have this Lochner's representation, right? Again, mu here is going to be more complicated. So mu is a operator value measure. We don't have to know what it is. The important message here is that we can write down every possible K that satisfies these properties. Relating this back to our problem, so we have a process x taking value in some over space H. We assume it's mean squared continuous, right? And we assume it's stationary. So in that case, the stationary covariance can be represented like this. So whatever mu you plug in, mu that is that satisfies what's described here. I left out some details. Whatever mu admissible mu you plug in, you have a stationary covariance operator. Moreover, suppose these kh is integrable, or the trace norm k is integrable, then you can do Fourier inversion and compute a bounded density for these for the cross-covariance operator. Yes.
Mu is trace class.
Yes, I'm assuming everything is trace class, and so I start out with trace class.
In the Lochner representation, this mu.
Yes. Trace class. Yes. So there's an issue of how to define this. If you're not in trace class, this is very tricky to define. So that's really part of the definition of this, what this interval means. Yeah, we can talk more about this if you're interested. I don't want to bore everybody. Oh, yes.
TX is inner product.
Which one?
This T to E to the ITX. This TX is inner product.
Right. So I'm assuming that T is in R. So if T is RD, then this is going to be inner product.
Yeah.
Trying to make the notation simple. Now, so is Matt? So people in functional data have looked at the case where there's a density, that a covariance operator has a density, and they, discussed how to estimate density, mostly using still the periodigram-based approach, extensions of that from time series analysis. So there are these papers if you're interested. In fact, the mathematicians have looked at cases of this problem You just have to figure out they're connected to what we do here. So these are papers in applied harmonic analysis. And if you look at the title of the papers, it's not clear how, whether how they're connected to our problem. And if you look at content, they deal with very abstract settings. And somehow you have to translate what they do to the kind of notation and setting we're used to. Anyway, so now, how much time do I have? Okay. So we talked about stationarity. Stationarity is great, but it's kind of limited, very strict model. How do we go beyond stationarity? So first, there's something called intrinsic stationarity, which is my title, and that's defined as follows. So let's consider a sign measure with finite support. So lambda is a measure that has mass c sub I at point t sub I. Okay? And for every function f, define f of t plus lambda as this convolution, which is sum of c sub I f of t plus e sub I. So for instance, if lambda is delta 0 minus 1, then this is just a differencing operation. So you can express differencing operations in terms of convolutions like this. And lambda k denotes the collection of measures with finite supports, sign measure rather, that annihilates polynomials of degree k. So, for instance, this measure here annihilates constants, function of constants, so it's a lambda 0. This annihilates any linear function that's in lambda 1, etc. Okay? So, George Matheron introduced the notion of stationarity after differencing. And he referred to such process as intrinsic random functions, IRF. Right? In particular, process which is stationary after one-time differencing, like when you subtract xt minus 1 from xt, it becomes a stationary process. Then it's called an intrinsically stationary process. And this is, intrinsic stationarity is widely assumed in Greek. And Matheron was the person who, sort of coined the term creeping. He didn't invent creeping. He's sort of, was the person who put everything together. He knew the theory as well as applications. Now, so we say xt is IRFK if this process x becomes stationary after we apply the differencing based on lambda. So xt plus lambda is stationary. For all lambda in lambda k, then xt is called IRFK. Now, the cross-covariance operator, of course, is simply this for this particular lambda, where C here is the cross-covariance of x. Right, so here we're assuming that this expression only depends on s minus t. That's what stationarity means. So this is kind of like linear basis function, what Grace mentioned this morning. Yes?
The notion for a second order stationarity, the second differences are stationary.
Oh yeah, so this is general, so this is lambda k. So for every k, this is defined. Now, So we said, you know, for RFK, we have that this function is only depending on s minus t. It turns out that there exists a k, which is called generalized covariance, which satisfies this relationship. So k acts like the covariance function, but it's really not the original covariance function. It's called generalized covariance by Matheron. And this is a somewhat complicated result. It's not especially deep, but it's if you haven't seen the proof, you will not find the proof very easily. It took us a long time to figure this out. Matheron mentioned this in his paper. He didn't provide proof. Nobody understood it. Everybody accepted that. And we finally proved it. But I think maybe Matheron felt it was very easy. I don't know. Now, as in the ordinary stationary case, one can write down a representation that's similar to Bachner's representation, like this. This looks somewhat different from the original Bachner's representation, that we have this quantity here, which will, allow us to have something, a measure that's exploding at 0, and for which the interval is still well defined. So I will not get into details of this, only that this is related to the Levy-Kinchin representation of infinitely divisible distributions of the characteristic function. One can also write down a spectral representation for IRF case. And this is a generalization of Clemaire's spectral representation for stationary processes. Okay. Some examples. So let's take a very simple case where the Hilbert space is actually a real line. The fractional ground motion introduced by Mandelbrot has this covariance. H here is called Hertz index. H measures the smoothness of the path of the process. Has many appealing properties. It's self-similar, stationary increments, and so on. So at the end, fractional ground motion is actually RF0. Generalized covariance is this quantity, which is the minus semi-variogram. And one can write down toy examples of IRF processes when H is a function space. For example, this one, which kind of looks like a Hundon-Laev kind of expansion. So these phi's are basis functions. The ZJs are independent fraction motions. And the lambdas are sort of eigenvalues. And for this, the generalized covariance operator is that. Now, I think I have a bit more time because we didn't start. My talk didn't start at 2:10. So I have a bit more time because I have part 3. I will just go over it very quickly. So here, that's the original paper Matheron wrote in the English language journal. Yeah, maybe the French journals are not really accessible. So this is a paper that everyone can read in events of applicability. If you can understand what he says, good luck. And eventually you have to go back to Bilfan and the Langkens book on generalized functions to know what the details of what's needed in the proof of generalized covariance. This paper is actually very helpful. It's a bit terse again. It really talks about a lot of things I presented here. Now the third part is my take of think globally, act locally. So I talked about global stationarity or global intrinsic stationarity. Those are more general than ordinary stationarity, but those are still rather restrictive. So I'd like to speak very briefly, perhaps in 5 minutes, about local stationarity. So let's consider a process xt. Again, for every t, xt is an element of a function space. So here I want to explore what happens when we conduct differencing locally at a point t. So let's fix t and see what happens when we do this as epsilon goes to 0. Suppose x has continuous sample paths, you'll say this will go to 0. But if we blow things up by multiplying something, suitable normalizing constant, it can go to a limit. Right? So this is very much like what we do when we take derivatives. So for example, if we have a return model, then when we conduct this operation, local differencing and then normalization, the limit is going to be fractional random motion, and the Hurst index is actually this smoothing parameter nu. And if BH is fractional random motion, then something similar happens. The normalization here depends on the Hurst index. The limit is still FBN. So FBN has a domain retraction in a way. Now, if X is multifractional ground motion, MBN, with Hurst function H, then at the point T, the normalization involves H of T. Here, H is same for every T, but since we have Hurst function here that depends on T, what is multifractional ground motion? Well, it's kind of like fractional ground motion, except the Hurst function changes with T. And here is a similar path for NBM with Hurst function that looks like this. When the value of the Hurst function is large, then the path is smooth. When it's small, the path is rugged. So I don't have time to really go through all my slides. I'm just going to quickly give you a summary of what's in the remaining slides. I'm going to consider this differencing operation locally for general lambda, not just the order one differencing operation. I'm gonna take the lambda in lambda k. And ask the question, suppose I can find normalization such that this generalized differencing converges to a limit. Okay? What properties must this limit have? In a nutshell, the limit is going to be self-similar because of the scaling. Self-similar. It's going to be IRF. So this is a notion of local intrinsic stationarity. And just like global intrinsic stationarity, I can have a representation for all the processes that are limits of this kind. I think Dennis is gonna scold me if I continue. So let me just stop here. Perhaps 30 seconds. So I have a toy example that I can show you. So let's say we have, sorry. Right, so this is really a function space. I'll tackle here. This is a process I constructed toy example. The phi j's are again basis functions, and these zj's are ID multipressure ground in motion. And how do we conduct inference on this process? Right? So what we could do is to do projection. So here we have a process. We can project the process on the function h. We're back to the real case. And for the real case, actually I've written a paper that talks about how to estimate the Hurst function. And we have a infill asymptotic result. If we have data observed on a fixed grid, then it is possible to prove a minimax rate, provided that the candidate functions are in the Holder class. The rate is very similar to what you see in non-parametric regression, with the exception of this extra square log term. And if you're interested in this, it's going to be in the paper that appear next year. The first paper here is the paper about sort of tangent fields, which are the limits of the difference process in the one-step differencing. So the person who studied this was Faulkner, and our results for general differencing can be viewed as an extension of that. So that's a useful reference. Thank you very much.
Yes.
So you found this generalized covariance.
Sorry, say it again.
You found this generalized covariance. So, but it looks like the negative of something. So this is basically like a negative definite function.
The generalized covariance, people describe it as conditionally yeah. So in the case of I0, the generalized covariance is the minus of centrifugal.
Because you say negative of something over symmetric.
Yes, exactly.
Okay, we learned what's
Well, it seems to me there should be great scientific interest in this data. I mean, it must be related to large-scale movement of the ocean that's related to climate, tectonic oscillation,
Yes,
you
absolutely.
build it in a physical model of the physics of the ocean, you should have some.
Absolutely. So here, sort of what I presented is really, non-parametric estimation is brute force approach. Doesn't involve any physics, doesn't have differential equations. So to be able to do that, we have to talk to specialists, to physicists, oceanographers. That will be our next step. He absolutely will.
okay. Mind you learn, don't fight percentages, right? So you need time, just give time. So especially when I have one paper under revision for the annals. So thanks Tyler for one talk. So time is a little delayed, so that's okay. We just probably just keep moving everything scheduled for 5 or 10 minutes. So we'll figure out how that goes. Our next speaker is a really famous person in machine learning. Okay? Alex Smola, who actually will be starting with page 1 and a half. He got PhD in physics. He got PhD in physics, which my physics means everything in my generation. Right? Chemistry is called applied physics. Biology is physics, but whoever can move. Right? Mathematics is simply a tool for physics. So physics is everything. So you got a degree in physics, that's bias anyway. From University of Technology from Munich, and got PhD from University of Technology in Berlin. Then he went to academic job, I think somewhere in Australia, so Australian National University, being a professor, doing really great. 2008 he went to Yahoo, and then 2016 became director of machine learning and Amazon Web Service. I personally bias. I don't like the word machine learning. I think it's more like automatic learning. Machine don't learn anything. So anyway, by that, interesting thing is when you look at his website, my final comment, you go to his website, give a name and address. Without saying anything, you say, I'm currently not looking for a PhD student. So see, you must do lots of confidence rather than say how wonderful I am. You say, I don't need more PhD. So by that, let's welcome Alex.
So thanks for the kind word and the introduction. The reason why I'm not looking for PhD students is simply that Amazon doesn't take PhD students. And yeah, sorry, nobody waste their time on that. So this talk forced me to, well, think back a little bit. We've been doing some work on graphs, mostly my team in Shanghai has. So a lot of the results are due to Zheng Zhang, Dan Zheng, and Mingyue Wang, also part of the team in Palo Alto. But this talk sort of forced me to go back and look at, what did we do with graphs before? And so, okay, a little bit of a bait and switch on you because I say, well, from features to kernels to features to backend, and I'll take a little bit of, engineering on you in the end. So talking about, frameworks, backdrop, that you said, graph backdrop partitioning, and stuff that are involved in this. And so, but let's start with something very non-threatening. Russian politicians. Okay, sorry, not threatening, maybe the wrong word, but so they do stuff with each other, right? And so you might want to do interesting things with that network. So for instance, you might want to find out what the relationship is between the vertices. You might want to find out, what the attributes of a particular vertex are. So such as you get some features, maybe you get some additional data, maybe you know the net worth of that person, maybe you know what time they send messages to each other and so on. And well, maybe in a slightly different setting, you might have a social recommend that, hey, you might want to take a bribe from that guy too, or well, don't trust this one. Or maybe use additional data, maybe biographical data to combine this. So that's the kind of fun that you might want to do with graphs. You can also use that for drug discovery and so on. So the big graphs are really everywhere. To some extent, I would argue that probably we have one of the largest places graphs available.
Aren't you missing Trump?
Yeah, I know. I didn't make that graph, but I would have wanted to put him in, but last time I did this after that, he got elected. That was in 2015 in that KDD talk. I made fun of Trump and he got elected, so it went badly. I don't know why I have this. But
was that based on real data?
no, this is just like, this is an interaction network of Russian politicians that I got somewhere, but this is just to motivate the problem so far. So what do we really have? Well, we have some vertices with attributes and edges with attributes, and then we have an estimation problem, namely given some vertex labels, you estimate the remaining ones. So for instance, who can I trust, who I cannot trust, or given some edge attributes, well, can I make some more? So for instance, which additional edges should I add? maybe they're timestamped and so on. So, and let's just simplify this even further. Regression on a graph. So this is like vertex labels, like yi and y, and I want to find some function such that function is kind of taking this a little bit liberally because I have fixed number of vertices, at least in the simplest case, so it's really a vector. But let me just call it a function for now, which maps the vertex ID into fi. And then I want to, for instance, minimize the loss, like the least squares loss, so fi minus yi for wherever I go. And so that gets me to a number of problems, like how do I infer the function values on previously unseen vertices, and how do I even define smoothness on this? And so one thing that I could do is I could just say, well, let me do feature engineering, right? So I have maybe some linear function, fi is w transpose vi plus b, and all the intelligence is now in those vertex features. And I could do a number of things, like the number of neighbors tells me something about how important somebody is. So I could just look at the degree, maybe the degree of the neighbors, and other things. I could look at a lot of different subgraphs that I can get. I mean, let's say maybe I take a 5-hop subgraph, and I get an entire vector of that, and that's walk to vec, for instance, and people like this. Or I can just overall fingerprint the k-step neighborhood, and this, actually the Weisfeld-Lehmann algorithm is a really great tool for that. And Carsten Borgward and Nino Shabashidze in their prize-winning paper, they use that to very efficiently compute graph graphs. So we'll get to the Weisfeld-Lehmann algorithm in a little bit, but it's actually an amazingly clever algorithm. Or I can just use linear algebra heuristics. It's not uncommon. Maybe I take my graph connectivity matrix and I factorize it, and maybe I take the leading few eigenvectors and I get some idea of what might be in there. Or I use PageRank, and PageRank turned out to be a multi-billion-dollar heuristic, namely the amazing heuristic that led to Google Web Search. And so I can do that. As an alternative, I can look at smoothness over edges. So I basically compare with some function gamma adjacent vertices, or maybe look a little bit further. And I can use Laplace smoothing. So the Fiedler vector and so on. John did some interesting work on that. So I can basically sum over I and j if I minus j squared, and then by simple trigonometry, that's just f transpose d minus gf. Forward. And if I don't like L2, I can try an L1 version. And so Krishnaiah Lecture and Ryan Tushirani, and I happen to also sit in on the meetings, but it was really Krishnaiah's work. You can do trend filtering on graphs, and you can look at higher order derivatives there. And this works quite well, right? I mean, it's this. So basically, at least you can construct data sets and situations where the L1 version beats the L2 version. Okay, so nice story, but it's expensive. So let's take a little bit of a detour. Once upon a time, there were kernels. So what does the graphical clustering have to do with kernels? Well, I guess that's the obvious part, namely, so what I can do is I can look at smoothness, and since I can use the graphical clustering to measure for smoothness, well, okay, I can, maybe think whether I could design some kernels based on that. And this, generalizes the finite differences, for instance, for a mesh, you have, the
target on the probabilities function directly, okay? Like the Lecture question LPA, okay, we just estimate probability directly. That's called soft classifiers, okay? So what are hard classifiers? The hard classifiers try to directly estimate the base rule without estimating pk. Okay? So I really don't care or don't estimate probabilities. For measuring problems, all I need to estimate is whether pk is greater than 45 or not. Okay? So we're actually targeting on a simple indicator function, or like a binary, function. So it's much simpler problem actually. I just, bigger than half or small. Bigger than 50.5 or not. For multi-class problems, okay, the goal is I want to know which class has the largest P. Okay, that is Archimed's rule. Again, I will not have knowledge about whether P is equal to 0.51 or 0.99. Okay, all I give you is a label. It's 1 because the probability is bigger than 0.5. Okay. So SVM actually satisfies. It falls into this category. Okay, binary SVM, just trying to estimate this sign function without estimating probabilities directly. Okay. So this actually is a hint-loss implementation, and it is a problem solved by a support vector machine or the binary classification problem. Just solve this optimization problem in the RKHS space, where the loss function is hinge loss, and for the penalty, you can actually put the RKHS norm, or you can also do like a lasso type L1 SVM if you want to do variable selection along with the classification. Okay. And so SVM is a very popular machine learning algorithm that has very many successful performance in practice. Okay. But one thing people actually like to show concerns about SVM or criticize SVM is it does not give us probability estimate. Okay. So in some sense, it gives me a label. It does not provide me a measure of uncertainty of your estimation or your label prediction. Okay. Or in other words, okay, what is the probability of this point belonging to this particular class? So that actually leads to my talk. Okay. The question is, the main question is, can we learn class probabilities using support vector machines? Okay. As I mentioned, SVM and logistic regression, they are fundamentally different. Okay. Standard SVM target on the base root directly without estimating probabilities. And so is it possible to make a soft classifier by using a hard classifier? Okay. And so basically, that actually is the problem I want to address. The reason, actually, before I continue, I want to use SVM to construct probabilities. Okay. Actually, there are a couple of reasons. First of all, I'm going to show we can actually, if you use kernel SVM properly, you actually can produce consistent estimate for these class probabilities without any model assumption. So actually, SVM, if you use it properly, you actually can provide a robust and consistent estimate for the class probabilities. The second reason is we know the beauty of SVM is computational efficiency. For high-dimensional data, the computational complexity depends on sample size mainly, not actually by the dimension of data. If you use a kernel trick, the QT problem you need to solve, it really depends on sample size rather than dimensionality. So in that sense, the SVM, its computation is much simpler. It will not actually affected by the dimension of the data. Okay, so can we learn probabilities using SVM? And the answer is yes. Okay, for binary case. Okay, and so this actually not actually our idea. Okay, this actually was first of all found by proposed by the paper by Wang and Shen in earlier 2000, actually later 2000. Okay, and so what is the main idea? Okay, the main idea is I know one simple standard SVM cannot give me the class probabilities. But what I'm going to do is I'm going to train my SVM multiple times. Okay, and each time, hopefully, it will give me some information about the probabilities. It's sort of ensemble techniques. Okay, if I use my SVM multiple times, and then I collect all the information together, I can construct the probabilities. Okay. Let me just give you some justification. Okay, how does this work? Okay, So when I say I implement SVM multiple times, question? Yes, please.
So in your loss minimization framework, if you use the loss to be the logistic loss, you get logistic regression, right?
Yes, yes.
So in that sense, I wonder whether, but you said that logistic regression gives you these class probabilities. So, but with the hinge loss, you get SVM. So is it kind of tied to the loss, whether you can get the class probabilities or not?
Say it again. It depends on the loss.
Does it depend on the loss? Is it what drives the fact that you can get class probabilities or not?
If you use a kernel logistic regression, you are saying instead of using a hinge loss, I can use a likelihood-based estimation, right? I use like a logistic regression. I can use a maximum likelihood estimator. Yeah, you can also get estimate. So here I'm talking about if I solve SVM, and is it possible to recover probabilities? Yeah. I'm not sure I really. We can talk about the question. Yeah. So there are other loss functions you can actually use to construct probabilities. But many of them you need some assumptions about the data, right? When you do the likelihood, you need actually assume what's the data distribution, what's the distribution of x, y, or y given x, x given y. So here, in some sense, because we are building the whole thing based on SVM, and it really does not require any data assumptions of the distribution of x or y. That's something that's without difference there. Okay, and so when I say I solve all SVM multiple times, I'm not really saying I just do SVM, solve the same problem multiple times. Instead, we're going to solve a weighted SVM. So here you can see I just modified this hinge loss function by using a weight. Okay, for all the points from class 1, I assign weight 1 minus pi, and for points from -1, another class, I assign from the pi, okay, the weight pi. And then I solve this problem. For each fixed pi, I solve this problem. Then you may wonder, so what is the solution to this problem? Okay? It turns out you can show when you choose a fixed pi, the solution to this problem actually is actually going to estimate another sign function. So essentially, I'm comparing T1x, which is the probability we want to estimate, minus pi. I essentially compare T1 with pi. Okay? And so how does this actually can be used to construct probabilities? Now actually I can change my pi, okay, by choosing a whole grid of a pi from 0 to 1. Okay? I basically solve multiple SVMs with different pi. And when pi equal to 0.1, okay, the solution tells me the probability is greater than 0.1 or not. Okay? It does not tell me anything about pi except tell me whether my probability for this point belonging to this class 1 bigger than 0.1 or not. Then I solve 0.2. It will tell me whether T1 is greater than 0.2. So if I keep actually solving my problems with using grid of pi, then there's a change point where T1x will actually change from, yes, it's bigger than this pi, then suddenly it will actually be bigger than a different pi. Okay? So here this actually is the algorithm. So basically we try pi 1, pi 2, pi n plus 1, and then for each x we detect a change point, okay, where at first P1x is smaller than pi q, and then P1x will be greater than pi q plus 1. Then I know my probability actually is captured by that interval pi q and pi q plus 1. Okay? And then if I do this with a very fine grid, okay, I can choose my pi at the grid point of 0.1, and then I can estimate T1 at the precision level of 0.1. Okay, but if I choose my grid at the thickness of 0.1, then my precision actually will be at the point of 0.1. Okay, so and then this actually the idea of like a weighted SVM for dynamic case. We don't know P1, we're estimating P1. We're estimating P1. So each SVM solution will tell me for this point, okay, P1x is smaller at first. Okay, let's say true P1 is 0.3. We don't know it, okay? We solve the problem with pi equal to 0.1. And then I apply my point to the solution. I got the solution. I plug my x into the solution, and I will get yes or no. In this case, because the true P1 is 0.3, when I choose the weight at 0.1, I will get answer is bigger than 0.1. Okay? Then I change my type to 0.2, then I will get 0.3 is bigger than 0.2. Then I change to 0.3, and I will say, oh, it's equal to 0.3. Okay? And 0.4 is smaller than 0.4. Then I know my px is captured in the interval 0.3 and 0.4. It's just like you just try to solve, capture, get multiple snapshots about the probabilities, then you combine them to actually to cover the P. Okay? So I think the algorithm is actually very neat and very simple. Actually, in the paper, in this paper, Wang and in 2008 paper, they compared this algorithm to kernel logistic regression, classification trees, and so on. It got very actually nice performance. And as I mentioned, you just solve multiple times, okay? And you don't need to make any data assumption or model assumptions about the probabilities. It's very robust, and you just solve complex problems all the time. And so this actually is how we make a hard classifier, soft in some sense, okay? And then the main so there are many advantages for this approach. It's model-free, and it's guaranteed to give us consistent estimation for probabilities. It's pretty robust, okay? Gaussian data or not, and it's scalable for high-dimensional data because you are solving SVM multiple times, okay? So what actually is our actual work along this line is how do we generalize this problem to multi-class problems when k is greater than 3, and if you have multiple class probabilities, how do you do it? Okay. And so multi-class problem typically, we have the way to deal with multi-class problem is instead of estimating one single function f, we're estimating a function vector f1, f2 to fk, okay? And each function represents the evidence that x belongs to particular class k. You can imagine f1 just like a kind of a logic monotonic transformation of p1, and f2 is p2 and so on. So when I take Argmax rule, we just can get actually classification rule for the particular points based on which k is the Argmax the largest component. Okay? And so there are many large margin methods developed for multi-class problems. Okay? Along this line, Grace and has also done multi-class SVM, designed different loss function, and based on this geometric margin to achieve again a base rule, okay, and for multi-class problems. And the answer is how do I use weighted learning, okay, for this multi-class problems, okay? And there are some challenges here. When we started this problem, actually, the first paper we did actually was 2010, okay, that's like 9 years ago, okay. And when we started solving this problem, there are many problems. So here, I'm going to show you 2 papers. Okay, the first paper was 9 years ago when I started doing this. I thought, it should be very straightforward, okay, since we have a weight before along this interval 0, 1, now I have multi-class problems. So my weight will not actually along the line search. So my weight, pi 1, pi 2, pi 3, pi k, and they actually be in a k-dimensional hyperplane, and the summation of pi as long as summation of pi equals to 1, and all the weight between equal to 0, 1, I can do it. And turns out in order to do that traditional way, and we need to solve many SVM, the computational problems, the computational complexity increases exponentially with the number of classes. Okay? And after we wrote this paper, okay, the paper was really published in JASA. We were really happy. We tackled all the theoretical challenges. Okay, they came up a way actually to show this actually works. Okay, and I'm going to show you. I'm going to spend 5 minutes talk about this paper. Okay, to show you it actually can guarantee to get a consistent estimate for multi-class probabilities and so on. But then I will tell you the limitation of this paper is it can only handle the problems up to class K up to 5. Okay, if you have more than 5 classes, and this algorithm takes forever to do. Okay, that's because the computational problem is really hard. And then actually 9 years later, we revisited this problem. It came up with another more scalable approach. Okay, to the same problem. So this is the idea of our JASA paper in 2010. Okay, let's just do this weight. Okay, now instead of doing a line search, I'm going to search this optimal weight. Okay, in this like a big triangle. Okay, in the 2-dimensional it's just a triangle, and 3-dimensional you have a finite dimensional hypercubes. Okay, and then we solve the pi, and we just solve it. We give a different weight for different classes, points from different classes. When I solve this problem, the idea is still I solve many SVM, weighted SVM, I combine them. Okay. The idea is there. And then it turns out there are actually several challenges. First of all, we have to define the new concept of, feature consistency in the classifier actually is consistent and asymptotic. You're trying to cover the base rule. So in order to weight the learning, the first thing we did is to produce the idea to propose the concept of high feature consistency. When you have a weight, okay, you actually have to use this notation, okay, what is the high feature consistency? And after we have this, we realize the hint loss does not work, okay? The hint loss is not actually high feature consistent if we don't have a dominating class. So then we have to do some other loss. So that's what we end up with. We use a truncated loss, okay? And we showed for this truncated loss, the solution to these problems will actually be guaranteed to have a high feature consistent. That will eventually guarantee the consistent estimation of class probabilities. The first thing we did is we have to design a new loss. Okay? The second thing we actually realized is whenever you truncate a loss function, you will lose convexity. Okay? The problem becomes non-convex. Okay? And in order to solve this non-convex, the weighted SVM, we have to use this ECA algorithm, like a difference convex algorithm. And then it turns out this problem, this algorithm does not give us because it's non-convex problem. Okay, I can get a local mean value and so on. Anyway, you can implement this. Okay, and we actually also have a very nice theoretical properties to show that okay, if you choose the proper truncation parameter for the loss function, if you tune the kernel with the kernel SVM, to tune the parameter properly, then you can guarantee to get the consistent estimation for all the probabilities. That's really nice, without any assumptions about data distribution or any assumption about the probability form. But as I mentioned, okay, this algorithm is not scalable, okay, because I have to deal with non-convex problems, and also because the scale of each QP is really large for the multi-class problems. We know that when K is large, when we solve this multiple classes problem together, the QP actually can be slow, and also the potential number of weight parameter I need to choose is really large. Okay, for example, for 5 class problems, if I choose my 10 weight points along each class, I basically need to solve about 10 can solve the large QP problems. Okay? And so the problem, so in the future we say, oh, although the theory is good and the performance is good for small classification problems, but we cannot handle problems with bigger classes bigger than 4. Okay? And so are there any alternatives, okay, which are more scalable? Okay, that is our actually second attempt. We just did it last year. I mean, yeah, the paper just came out. The idea is, divide and conquer. So what if I don't do multi-class problems simultaneously? I decompose my multi-class problem to multi-binary problems. And as long as I do them correctly, and hopefully I can still recover my multi-class probability so reasonably, consistently. Okay. And so the good thing is, if we have multi-binary problems, we already know how to solve weighted binary problems by solving complex problems. Okay. So this is the idea. Okay. This is the idea is instead of doing multiple K classes problems simultaneously, I'm just solving two binary problems, okay, for each pair. Okay. So basically, I'm going to define a new label, okay, called RKK prime. So basically, I'm just looking at class K versus class K prime, I say each time. So for any fixed pi, I'm only solving this weighted learning for 2 classes, class K versus class K prime, okay, and I solve the problems. Okay. Then you may wonder, okay, so what is the solution to these problems? Because originally you had K class problems, now you only look at the 2 class problems. What is the solution? And it turns out, okay, we can show that, okay, the solution to this weighted learning problems, actually, to these problems is equal to this, okay? It's equal to Q of K given KK prime. Okay, so essentially, it gives us the probability of my point belonging to class K, given that this point has to belong to either K or K prime. Okay? And so that is not our P. PK prime are our targets. But now we actually change the objective function from P to Q. Okay? But the nice thing is, there is a very interesting relationship between Q and P in terms of their ratio. You can show that the ratio of QK prime equal to PK and PK prime. It turns out, if we use this relationship, then we can solve this weighted learning by estimating many Qs, then we can recover P. Okay? And that's actually what we did. We solved many multiple binary classification problems, and then we actually construct my probability, multiple probabilities by using solutions to those binary problems. By putting all these pieces together, we actually can recover this. Okay? And so it turns out it's really scalable because we only solve 2 classes problems simultaneously at one time. So it's parallel, very simple parallelization. And for each problem, it solves multiple weighted SVM. It just gives small QP problems. And because I do this weighted, they can all be parallel. So the whole thing actually can be easily paralleled. And so this actually we call it the divide-and-conquer method. And so essentially we're just trying to estimate these class probabilities by usually dividing the multi-problems into many binary problems. And again, we can prove that, okay, and the solution actually is guaranteed to be consistent for the 2 class probabilities as long as the kernel SVM include the proper kernels. Okay. I think I'm running out of time just to show just the quick comments. Okay, it's convex optimization, parallel computing, and we need to choose the lambda, we generalize the cover bigger distance to choose lambda, and improve conversion rate. I think I just give you an example to show how this actually algorithm compares to the popular logistic regression, baseline trees, kernel logistic regression, and just to give you an idea how this method works. Okay, this is going to show you some simple simulations, 3 class classification problems. Okay, so the first 2 actually 2 columns are our new divide and conquer approach, and the So WZL, the third column, that's our JASA paper, okay? And that's, theoretically, they are all guaranteed to be consistent. But here I'm just going to show you the finite performance of these approaches. And the fifth column is the kernel logic regression. Okay, that's pretty flexible. But you can see, and then the sixth column is the tree, the last column is the oracle. So this is just a kind of just give a mean square error prediction for the probabilities. And you can show the direct contour approaches work really, really good, close to oracle, and better than JASA paper, and also better than the kernel logic regression and the trees. I have this consistent observations for forecast problems and non-linear classification problems. If you want to know more details, you can read our paper. It just came out last month, actually. And the 5-class classification problems, they come really well. And for the real data, okay, and we actually tried different, even larger number of classes, like 10 class or 4 class and 5 classes. And the good thing about this algorithm is you don't need to do variable selection or dimension reduction, because SVM can handle that directly. So we actually tried 4 benchmark data set here, and so for different classes of problem, you can see the real Epson actually are also among the top performance of these approaches. Okay, and for this real data problems, actually random forest does really well also. Actually, you can see this is our new approach, and this is random forest. They're actually very close to each other, but they are also top 2 performance. And then, and as I mentioned, the method can be applied to heavy mental data directly. So we actually applied this algorithm to this microwave expression data where we have 2,000 genes for class classification problems, and the performance is also pretty good. I think I was just stop here. Take home message. Okay, so this actually is a model-free probability estimation approach for multi-class problems. So just now, people tell you SVM cannot really do probability estimation. You can say no. Actually, you do the weighted SVM. Actually, it can recover binary or multi-class problem consistently. And the future work, we are working on functional data actually analysis. So functional data, the logic regression is really hard. Actually, using this technique, we don't need any assumptions. We can be applied to this functional inputs straightforward. I'll stop.